Okay, so what if a bridge could tell you it was feeling stressed? I mean, not after an hour of some supercomputer crunching numbers, but right now, in real time. Well, that's the promise of a brand new AI that can simulate the massive forces on our infrastructure almost instantly. Let's take a look at how it stacks up against the old way of doing things.
For decades, figuring out structural stress meant you had to wait. A lot. The traditional method, which we're going to get into, takes hours for just one simulation. But this new AI model, yeah, it can spit out an even more accurate result in a matter of seconds. And look, this isn't just a tiny improvement. We're talking about a leap from hours down to seconds. That kind of change, well, it unlocks a whole new world of possibilities.
All right, section one, the simulation slowdown. So to really get why this is such a big deal, we gotta understand the problem engineers have been banging their heads against for years. For decades, they've been relying on a method that, yeah, it's super powerful, but it's also painfully slow. And it's the thing that makes sure our world, doesn't fall down.
And that method is called finite element modeling, or FEM for short. The easiest way to think about it is like building a bridge out of digital Legos. You take a super complex structure, you break it down into thousands of tiny simple pieces, and then you solve the physics for every single one. And look, it's the gold standard for a reason. It is incredibly accurate. But, and this is a big but, when you've got something moving, something dynamic like a train going across that bridge, FEM has to recalculate everything for every single moment in time, over and over and over. And that, as you can imagine, is just ridiculously expensive from a computing standpoint.
So naturally, people have tried to throw AI at this problem before. But those early models, they had some major drawbacks. For one, they could really only predict the stress at a few specific spots, maybe where you'd put a sensor. They couldn't give you the big picture across the whole structure. And they really struggled to show you what was happening continuously over time. But the biggest problem, most of them were just learning from data, which means sometimes they'd come up with answers that, well, they kind of bent or even broke the fundamental laws of physics. Not exactly something you want when you're designing a bridge, right? Okay, section two, a smarter AI architect. So all those problems are what led researchers to build a totally new AI architecture, something designed from the ground up to nail this specific challenge. It's called the Multiple Input Operator Network, or MIONet for short. So how does this thing actually work? Well, MIONet has this really cool design. It uses two specialized brains, you could say. First up, you've got its spatial trunk. Think of this as the where brain. It learns the actual physical shape, the geometry of the bridge. Then you have the temporal trunk, which is the when brain. It processes how things are changing over time. So MIONet takes in the input, the load and its speed, and then it combines what these two separate brains have learned to predict the entire structure's response. It's pretty slick. And that right there, that's the key innovation, this idea of decoupling. By separating the problem of where from the problem of when, the AI can learn each part way more efficiently and then just elegantly stitch them back together. Honestly, this is the secret sauce that makes it so much faster and more flexible than any of the AI models that came before it. Section 3, teaching AI the rules. But listen, being fast is one thing. It also has to be right. And this is the really clever part. MIONet isn't just learning from a bunch of simulation data. No, the researchers are actually teaching it the non-negotiable, fundamental rules of engineering. And the main rule here is a concept called dynamic equilibrium. It's a core principle that goes all the way back to Newton's second law. It basically says that for any structure, at any given moment, the forces pushing on it from the outside have to be perfectly balanced by the forces resisting from the inside. Its mass, its ability to dampen vibrations, and its overall stiffness. So the researchers literally encoded this law right into the AI's training process. They took the math for mass, damping, and stiffness, and as the paper puts it, they baked them directly into the loss function. Now, in the world of AI, a loss function is basically a penalty system. It's what tells the AI how wrong its guess is. By putting the physics right there, they're not just penalizing a wrong answer, they're penalizing a physically impossible one. So what does that really mean? It means the AI can't just find some random pattern in the data and call it a day. Nope. It is fundamentally constrained by the laws of physics. It's being forced to generate answers that respect how the world actually works. In a way, they've taught it to think like an engineer.
All right, section 4, from beams to real bridges. So we've got a fast AI that also knows the rules. Sounds great in theory, right? But how does it actually hold up in practice? Well, the researchers put it through a series of pretty tough tests.
First, they started simple. They threw a 2D beam structure at MIONet, kind of like a basic bridge you'd see in an engineering textbook. And yeah, it passed with flying colors. It perfectly predicted how the beam would bend and twist under all sorts of different loads and speeds.
But then came the final exam, a real-world, complex, 115-meter-long steel arch railway bridge in Belgium. This wasn't some simplified model anymore. This was the real deal, with all of its messy, real-world complexities. And the results? They were absolutely stunning. MIONet's predictions were over 95% accurate when they compared them to those super slow, gold standard FEM simulations. So first check, it was getting the right answer. But here's the real kicker. It wasn't just accurate. It was more than 100 times faster than the traditional method. 100 times. This is where you really see the jaw-dropping power of this new architecture.
Let's actually put that into perspective for a second. A simulation that would normally tie up a powerful computer for an entire hour, MIONet can now do in just 36 seconds. Think about that. What used to take 60 minutes now takes less than one. It's just a completely different ballgame.
Section 5, the digital twin future. Okay, so what's the big deal with all this speed? I mean, why does getting an answer in 36 seconds instead of an hour matter so much? Because it unlocks a concept that honestly has felt like science fiction for years: the digital twin. A digital twin is, well, it's exactly what it sounds like. It's a perfect, living, virtual copy of a real-world object, like that bridge we've been talking about. And this isn't just a static 3D model. Oh no, it's a dynamic replica that updates itself in real time. The one thing that's been holding this concept back for huge structures was the simulation speed. I mean, you can't have a real-time twin if your updates take an hour. But with MIONet, now you can. And this is where it all comes back to us. With digital twins powered by this kind of AI, we could literally monitor the health of a bridge with every single car that drives over it. We could spot tiny fractures years before they become a danger. Engineers could test thousands, not dozens, but thousands of new design ideas in a single afternoon. And maybe most importantly, after an emergency like an earthquake, we could know in seconds if a critical bridge or building is safe to use. This whole breakthrough is a massive step towards a world of smarter and much, much safer infrastructure. It really leaves us with a pretty fascinating question to think about. What if every single bridge, every skyscraper, every power plant, what if they could all tell us exactly how they were feeling? Not once a year during an inspection, but every single second of every single day.